Hello everyone, this is part B from my previous video. I think it's 3B. I think I got it wrong in the previous one. Anyways, just to recap, it's about this circuit here. We've got our soldering station tip. I'll call it a soldering station tip. Hang on, well, let's change this because there's a reason. Yeah, a soldering station tip. This is one of the modern tips, and it has a coil of wire as a heating element inside, and it does not have a PTC. I've added this now. You will find in the cheap fixed temperature soldering irons that the element inside those may have a PTC element because it's the way that works, and you add current, it heats up, its resistance increases, the hotter it gets, and as the resistance increases the less current gets applied. So then it comes up to a balanced temperature which is determined in manufacturing, and it stays at that temperature. So that's how a PTC element works. We want to be able to adjust the temperature of the heating element. So this is the normal symbol, but like I said before, I wanted to show that it is a actual coil of wire that gets heated up, you know, like you see on the old bar fires where you had this little glowing wire ring, and that's what's inside one of these. And we've got our thermocouple. So that's just a recap, and we want to measure our voltage from our thermocouple, and so we're going to use this circuit here. So I've already been through that, so I'll just pause it a minute. Right, I'm back. So this part B is about the code we're going to use on the microcontroller to get a temperature from a thermocouple. And I'm going to, like I say, I do like comments, and I've put lots of comments in this code because I tell you, I can't remember it all, and I need refreshers. And if you don't put comments in, you'll forget why you're doing something or the reason for it. You may give it a really nice good name, but that name just tells you what it is, but you may want to know how that bit actually works. So I always start off with a comment at the start, just telling you about what the program does, or my license. Basically, if you ever use my code, basically this is my license. Give credit where due, and that's where this here I should really put here Arduino. This is the Arduino library. We're using Arduino on this. I'm using the Arduino architecture here. Well, I said Arduino's in brackets, but I am just using the Arduino architecture. I don't need any interrupts or anything. It's just all Arduino really here. So this can be actually you should be able to put this on any Arduino microcontroller. Yeah, so it was written for the Tiny. And the reason why I use these little cheap microcontrollers, I pick them up, they're about a quid each, and say like this project, at one point we're going to add something like 20 volts or maybe 24 volts to a MOSFET, which we are going to control by a microcontroller to heat up the element. And the reason I use this cheap Chinese stuff is I have a habit of getting it wrong. You move it. Sometimes I tend to move wires live on my breadboard, and sometimes I'll hit the wrong wire and it totally fries it. But because they're like a quid a piece, it's not an issue for me. You know, it's the cheap little modules, and so if I fry one, it's no heartbreak to me basically. But I'd rather not fry one. But that's why I start off with little cheap little microcontrollers, and then as the project progresses, then we can move to a more expensive processor. Well, I say more expensive, maybe one that costs maybe 3 or 4 quid. Okay, so anyway, we'll continue. So, and I always sort of tell you what it does in the code's going to do. So we're going to show a value displayed on a 4 times 7 segment display with the common anode, based on the output value of an op amp converted to degree C. The calculations are derived from the calibration values taken. So here, I'll come to this. Now we are getting a voltage from the a K-type optocouple, and this is in millivolts. Now there is a linear. Right, okay, I forgot to do something. I just remembered. There is a linear slope on it with a relation to voltage and temperature, so we can actually calculate the actual temperature we should be getting from a voltage that we receive from the from the thermocouple. But there obviously we're on a breadboard and things, and there are some discrepancies. We have a few resistors in there and things, so we have to compensate for those. And then there is also, I've mentioned this before, there is the cold junction, and I have no clue what that is in our setup. So, but there is a workaround. There is some maths. Oh dear, I've said maths. There is some maths that we can use to calculate the cold fusion voltage, and we need this cold fusion voltage form. I don't know if you watched Richard's or my previous video. I sort of said, I wonder why we're getting a negative voltage here. And the reason we were getting a negative voltage is because we haven't incorporated the cold fusion voltage. You need to add the cold fusion voltage onto the hot fusion voltage to get a positive value. I'll explain a little bit more in a minute. So let's continue down the code. So we need an EEPROM. The reason I'm using an EEPROM is because I want to save the calibration value that we get, so that we don't have to calibrate every time we turn on the processor, the code. We just calibrate the thermocouple once, and once we know what the calibration is, we save it into a section of memory on the microcontroller. This is just my debugging. Like I say, I mentioned I'm using this tiny 88. This has no serial port. It has no UART, so we can't put a UART through a UART to USB serial. So we can't do things like print this value, print that value. So what I have 3 coloured LEDs, and this helps me debug. And so basically in the code, what I'll say is if it is this, then light the green one. If it's that, light the red one, and then I get a visual representation of what's happening in the code and seeing if it's working okay. So we can forget that bit there. So now we've got the K-type thermocouple, and we need some values here. And I've put the notes here. So this thermocouple pin, which we're connecting to A6, which is an Arduino thing. This is analog 6 on the Arduino. So a pin has been defined as an analog pin, and we can get a value from this pin. And so this thermocouple pin just says we're using A6, basically. That's from the input to the microcontroller. So if I look at the circuit diagram, so this output from the op amp goes to our microcontroller, and it's connected to this pin A6. So we've got another value here. So we're talking about a K-type thermocouple, and the K-type thermocouple has certain characteristics. It will do certain things when certain things are applied to it, basically, and these are known values. So the slope, which is basically is how many millivolts the thermocouple puts out per degree C. Now you can see that it's 2.31 millivolts here per degree C. Well, that isn't what we were reading. This is more like after the op amp. But anyways, it's a value and we're using it. But then we've got, so well, I've written there what it does, so you can read this. I tell you what, let's make this bigger. Let me just make the text a bit bigger. I don't know how it might be viewed on the screen you're watching on. There, that should be more readable. So now you should be able to read this, okay. And then we have the intercept, which is millivolts again. It's the voltage offset when the temperature is at 0 degrees Celsius. So well, I could stick it in the fridge to find this, but or the freezer, shall I say? But well, if you've got your machine built up and you're not going to stick your machine in the fridge to get the zero the Celsius, so this is the value basically. So it's a constant value. It's set that is what the it's supposed to be for a K-type thermocouple basically. So and then we've got the cold junction temperature, right? Like I said, this is not not known at the moment. To do this, we need to do some calibration to find out what the cold junction temperature is. I've written here. Yes, so it's where the wires connect to the micro. So if we look at I showed you on the other thing. That's another drawing I didn't. Hang on, let me just pause. Right, there we're back. Yeah, so it was this picture I forgot to get. So remember that we have a junction here. This is our, well, actually, it goes all the way back to where our microcontroller is. So well, it's probably at the upper amp actually. So it's the cold, it's the temperature when it's the value we get at. Actually, I've just thought of another thing. I'm just going to do a search for one of Richard's videos. It might explain it better we're about the cold junction temperature and the hot junction temperature. So basically we've got the two wires, and at one end we're going to be measuring a voltage, and at the other end we're measuring a voltage, and we need to know the two voltages so that when we read the voltage at this end, we know what to add to the other to get the correct voltage. Let me just pause again. Okay guys, this is a clip from Richard's Why You Shouldn't Use an Auto Router, and we're about, where are we? 23 minutes in and 42 seconds. And what he's doing here is using his millivolt meter to find a short. What he's doing is putting a current on the input and then following the traces through until the millivolts drop. And because the track is a good length from, I can tell you the fault's down here somewhere, but if you watch this you'll understand why we have a cold
these 140s, let me find somewhere. No. What I'm going to do is I'm going to turn the power supply down.
Right, I'm going to leave it there. Let me just get rid of this. I recommend watching that video. And what he's doing is using a power supply, applying a current to one of the tracks on the PCB. And if you imagine when he's at one end, the current will be that the voltage will be a few the current will be a few milliamps greater than it is at one end than it is at the other end. And where it starts to come towards a short, say these two wires were connected together, then the voltage is going to drop. So we've got a length of cable where we have a low voltage at one end and a high voltage at the other end. And this is what I'm trying to explain about the cold junction and the hot junction. We'll have a voltage drop because we're talking really small millivolts, tiny millivolts. There's going to be a drop along the length of the cable. So we need to know what that drop is by measuring the cold fusion end compared to the hot fusion end. Find the difference, and then we can use that in our calculations. I hope that made a bit of sense. Let's get back to the code, and I'll explain how I find that. So yeah, this is the cold junction temp, and this is basically what it is the difference between the hot end and the cold end of the wire. So it's going to be a fixed value. Once we do the calibration, we'll find out what that cold junction temperature is, and we will stick it in the EEPROM and save it for whenever we use it, basically. Now I have a buffer for taking readings. Now I'll explain the buffer when we start using it. But basically, there's going to be 10 readings taken from the op-amp. So from this value here, I will take the 10 last readings. We'll add them all together and divide it by 10 to get an average of the last 10. Basically, we're not going to read an exact reading. We're going to get an average of the last 10 readings that we take. So we need a small buffer to stick all those readings in. This is all to do with the I'll explain later. So then we've got our 7-segment display, and the pins for the 7-segment display. Well, I've done all that already for the 7-segment display. That's all to do. And our setup is just the same, but except for this one. This is what we've added now. So what we've added is this bit of code. There's in our setup, we need to know if we're in calibration mode. And we set that by defining calibration mode, and that is up here. There. So if I undefine that, if I define that, right, so we've got, if we now put it into calibration mode, when it comes to this point here, where are we? Shit. Where? Oh, I'm in setup. There we go. Yeah. So now we can see. This is another thing. Well, I'm sure I've mentioned it before using Visual Studio. Calibration mode. So if calibration mode is defined, it will run the calibration mode. So I will explain calibration mode. I'm just going to turn that back off because I want to save this as I've already done calibration. But what I'm going to do here is explain why we have a calibration. So I'll just turn that off. To turn it off, we just comment that out, basically. So if I comment that out, and then we can see down here, where are we? Setup, yeah, there. We can see that it's now grayed out because we're not going to use it The compiler knows not to use that anymore. Yes. So we do if we're going to do calibration, we go to calibration. So in calibration, what we need to do is we need to know what the cold junction temperature is. This is what we're finding. So there's another function, calculate cold junction temperature, which is down here, this one. So what we need to do is, once we've built our little thermocouple linked to our operational amplifier, we need to read some voltages out of the operational amplifier to at certain temperatures. So at temperature 100, we'd heat the tip up to 100 degrees C. So I'll be using another temperature sensor to find out what temperature the tip is, heat it up to 100 degrees C, and take a reading from the op amp, which here in this case was the voltage at 100 degrees C was 400 milliamps. I've only done it 2 times. I found 2 times was enough. So what I've done is I did one at 200 degrees and got this value, and I did one at 300 degrees and got this value. So with them 2 values, which is our calibration temperature there, voltage, so we use them 2 voltages, we use the intercept, which we've already set in our settings, and we know the slope. So I've put a note here to calculate the temperature differential delta T for each calibration point. These represent the different temperatures corresponding to the calibration voltages. So basically, we have to find these. Like I say, you have to heat the tip up, find out what the voltage is out of the operational amplifier, and write it in here. So this won't change. What you'll do is you'll alter this to the actual value that you read on your multimeter at this temperature. Same here, same here. And then we get the delta T of using this formula here. It's pretty simple maths. I mentioned maths, but you take one from the other and divide it by this. Then once we've got the 2 delta T's, we find the average. So basically we just add in these 2 together. We take the delta T from the temperature, and then we add the 2 together, divide by 2, and we get the actual returned value. This returns this value function to here, and that gives us our cold junction temperature, which we've found out now. Now that we know that, we can then save that into the EEPROM, and that's what we do here. So once that value there has been calculated and saved into the EEPROM, we can work out we can convert the millivolts into degrees C. So let's just go back to where calibration there, and if we're not using the calibration, if we've done it already, we've already got the value in the EEPROM, so we don't need to do the calibration if we've already put the value that we worked out previously. But so what we do is we get from the EEPROM the cold junction temperature, and that's what this bit does. So it does it after the calibration, but then once it's done and it's in the memory, because the EEPROM is it's electronically erasable programmable read-only memory. There we go, I got that out. So basically, if you turn the microcontroller off, this value still stays in there. We can. It's a bit of memory that it's a non-volatile memory. It stays there. for, I don't know, 20 years. Oh, yeah, right. I say 20 years and you think, oh, right, in 20 years' time it's going to disappear. But no, it's 20 years of use. Okay, right. So, yes, so we only do the calibration once, and then once we've got that saved in the EEPROM, we can always use that value from EEPROM, and so that's what we do. We get it. So this is the loop. Now, pretty simple, really. It's just another bit of maths. This, right, depending on the microcontroller that we use, it will have an analog to digital converter on it. The one I'm using is a 10-bit analog to digital converter. That means it can go up to a value of 10 bits, which is this value here. It can count up to 1023. Well, 1024 if you count 0. This is why you often see the 1020 form of memory. It's because it's 10 bits, and I've put some notes here again. So basically, we're converting the millivolts, which is analog, to a value between 0 and 1023. So because it's digital, it has to be a number within this range. But that's because we're using a 10-bit analog to digital converter. If we use a better one, we could use a 12-bit. We could use a number between 4096, and that will give us a much higher resolution of conversion. So yes, that's all we're doing here. So we've got our output voltage is the analog value, which we have read here. So this analog value is the actual reading we've read from the thermocouple pin, which we set on A6? Yeah, on A6. Oh God, I've lost my place. There we go. Yeah, so pin A6, we read what value, what millivolts is on there. We set this value at that value, and then we sort of multiply that value by, because we're supplying 5 volts. Now, right, let me just pause again, because I've forgotten something else. Yeah, I forgot to get this picture again, this circuit. Yes, I thought this is a good time to mention this reference voltage. See this pink area, this reference voltage. This is giving us an active when you power something, and you say you power it with 5 volts, you might get like a voltage drop through certain components. And so you don't get an exact 5 volts, and so if you're referencing the 5 volts you're getting from the power supply, it may fluctuate and change, which is also going, because what we're doing here is we're using the 5 volts here divided by this, and so this will end up fluctuating, which we don't want. So what we do in the circuit, we add an actual voltage reference. So if you see this little chip here, this is our reference voltage, and what this does, it gives a very stable voltage out. We can set it to what voltage we want, but it is what the voltage we set it at, this stays at that voltage and it doesn't fluctuate. It's what you could say, it's a precise voltage as a reference. And so what we will do eventually is add one of these chips, and it goes into another pin, which is, there is a actual, the microcontrollers usually have an actual pin for the reference voltage, so that the analog circuit, the digital the analog to digital circuit can work more precisely. And what we would then do is use this reference voltage here coming from this chip. But for the time being, we're just doing it Arduino, and Arduino has an analog pin, and the reference voltage is the power voltage going in, which actually it's probably about 4.4, because it goes through a if you get say an Arduino Nano, it will have a protection diode on it, and you will get a voltage drop through that diode, and the actual processor will probably only running at 4.4 or something like that. It won't be running at 5 volts. It'll probably have a voltage drop of 0.6 or something like that. And so this actual value that I'm using here is wrong. This is the theoretical value I'm using here. But like I say, to get an accurate reading, we would use one of these chips and use the voltage value from this chip. So if this chip was, say, doing 1.2 volts coming out here, what we would do is we would alter this value to 1.2 volts. As it would be the same as our reference voltage. So I hope that I'll just move that there so you can sort of pause it a little bit and have a read of my notes. I find it better to write notes than actually try and speak them. I'm not a good talker. Right, okay, so this is how we work out the output voltage. We've converted it to a digital voltage now here. It's a float. It's some point something. So once we've got that, then what we need to do is work out the actual temperature. So we've got a function for that, which is here. So basically we've got our two inputs, we've got our output voltage, and we've got our cold junction temperature. This is why this was very important, because what we're doing is we're taking one from the other. We're adding one to the next. So once we've used our output voltage and we've done our calculation using the intercept and slope, we get the temperature difference to calculate into an actual temperature. We also need to add it to the cold junction temperature that we've worked out when we did the calibration. So this function will return both these two these values added together. We work one out and then we add the cold junction, which is this cold junction is after calibration is actually stored in the EEPROM, which you need to do. If this isn't in the EEPROM, then the program won't run, because if it's missing, it'll come up with an error. Okay, so it returns the value. Let's go back to where we were. Was it up here somewhere? Yeah. No, it wasn't. We were down here. Yeah, so once we just calculate the temperature, so this returns. Oh, well, I'm not going too far. Where am I? Oh, was I in the loop? Oh shit, I forgot. Oh, where was I? Oh, here we were. Yeah, get the actual temperature. Yeah, we're in the loop. Yes. So once we get the actual temperature, we stick this into the buffer. We need at least 10 readings, because the buffer's got 10 actual segments. And what this is a circular buffer. Now then, what we don't do, right, okay, so I'll try and explain the circular buffer. I'll just move this down. Let's put some comment in there. No, I don't need that down, do I? Right, so I'll put some comment this is so I can type. Right, so what we do is we take, like I say, we take 10 readings. So what we don't do, so say we take a reading of 400 millivolts, then 410, 405, and then maybe 395. What we got? Right, say it's up bouncing around that. We've got. I'll just do another one, and we'll go 390. Right, and then say we get some similar readings. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what we don't do is take 10 readings and then add them together and then divide by 10, and then we get the average. We all know that bit of maths. Where are we? Average temperature, which is all this lot added together and then divided by the buffer count. There, this is the maths. That's what I've just said. So we add all them together, we get a value, then we divide by 10. That's what this bit here is doing. But what I'm trying to say is we don't get the 10 readings and then do this and then get another 10 readings and then do this. What we do is, it's a circular buffer. This buffer, what we do is we get a reading and we add it. So this could be 401 and we remove that one, and then we take them 10 readings, add them together and then divide by 10, and then we take another reading. It could be 410 again, and we remove that one, and then we add these together. So basically what we're actually using is we're still using the previous reading each time, but what we do is this circular buffer, it adds a reading in at this end and then removes one from the other end. So it's first in, first out. First in, last. Sorry, is it last in? Last in, first out. Well, I'm sure you get what I'm on about here. So basically, we just keep adding and removing, and then so basically, it's the last 10 readings that get used, basically. Okay, so I think I've waffled on about that enough. I'm sure you've got that already. And then we calculate the average, and then what we do is we update display, and I've already done display, so all it does is display the temperature that we've calculated here, and that's it basically. So that's how we display a value that we've got from a thermocouple through an operation amplifier, the output of which we then input into the microcontroller. It converts it from analog to digital, and then it calculates the value into degrees C and displays it on a 4x7 segment display. Although this one it only uses 3 displays. In my display I had 4 because that's what I had, so I did a 4 one. Okay, so yeah, I'm rambling again. I'm going to stop it there. Okay, I hope that was of some interest to somebody.